In the previous lecture, we have seen that how we can count or calculate the probability of any event, and how to calculate the space, sample space, and then using the sample space, we are able to calculate or count the number of favorable outcomes for an event, and then if we know what are the number of outcomes in an event, then we are able to calculate the probability of that. Okay, so here we have calculated the probability using the sample space, which is a traditional definition of a probability. Now we'll try to extend this idea to the problems or to the questions when the finding sample space become a tedious job. Okay, so then what we can do? Okay, so then how we are able to find the probability of the event? Okay, so let us try some examples. Okay, so we'll go with the example. Okay, so we have seen three random games or random experiments. One was a coin tossing, other is the rolling of a die, and the third is the playing cards. Okay, so now we will see the example based on the playing cards. Okay, so what will be having a well shuffled, you can say a card is drawn from a pack of 52 cards. Then find the probability that, okay, first the card is read, second the card is face card or chair card, the card is that. Okay, so these are the different events, and we have to find out the probability of each of this event. Okay, so here if I try to write the sample space, then sample space is this 52 cards. Okay, so in the previous example, we have considered the sample space of 36 sample points, or this is a sample space of 52 sample points. Now let us see this one by one. So we have a pack of 52 cards. That means this is our sample space. And what we are doing, we are drawing a card at random. Okay, so we can add it at random. Okay, so we don't know um, how we are drawing the card. We are just picking up the card at random, and then we want to find what is the probability of this events. So, and to understand the probability of this event, we need to understand pack of card that we have discussed. So we go with the solution. Okay, so what we'll be having? Let S be the sample space of drawing a card at random. Okay, now what we are having? So we can have number of ways to draw a card from 52 parts is equal to. So what we are doing here, see, we have 52 cards and we want to choose one card. So it is a simple, that's going to be 52C1. Okay. So C is a combination and that's why out of 52 I'm choosing one, and this is going to be 52 ways. Okay, now here we need to see some of basics of our combinations. So what we know about the combinations, see how we define NCR. So N is always greater than R. So NCR is equal to N factorial upon R factorial into N minus R factorial. And some basics of this are as NCR is same as NC minus R. Then we know NC0 is equal to 1, which is same as NCN. Okay, and then we can calculate some more the basics ones. Okay, as we know NCN, we have calculated, so NC1. If I use this formula, then I am having N, then I'll be having NC2. So I'm having N into N minus 1 by 2 factorial, which is 2. So these are some of the basic formulas for combination. And here we are choosing one card out of 52 cards. So we have, this is NC1 is going to be N, and that's why we get this is going to be 52. So if I use this formula and try to calculate, then see how we are able to get this. Okay, so I'll show you by using this formula. So this is our N and this is our R. So what you'll be having here, this is 52 factorial upon 1 factorial into 52 minus 1 factorial. So it is going to be 52 factorial into this 1 factorial is 1, and this will be 51 factorial. And hence what we'll be having here, this is 52 into 51 factorial, and then we have this is by 51 factorial. So this 51 factorial will get cancelled, and I'll be having this is 52, which we can easily say directly NC1 is equal to N. Okay. And hence here I can write this as, so we get this number of ways, that is going to be 52. So by using 52 ways, you are able to draw a card from a pack of 52 cards. So these are the sample points we have, or this is the number of points in a sample space. Okay, so I got here, this is number of ways to draw a card. Okay, so that's what we know now. Okay, so these are the number of ways. So this is going to be N. Okay, now what is the event we have? Okay, so see the event. The first event is that the card is read. Okay, so what we consider is, so let A be the event that the card is read. Okay, so now tell me how many red cards are there? How many red cards are there? Yes. So there are 26 red cards. And then out of that 26 red cards, we are choosing one card. Okay. So then what will be the number of ways? Okay. So that we have to define. So let A be the red card. Then what we know is there are 26 red cards. Okay. And then what we have to do is, now number of ways to choose one red card out of 26 is equal to, so simply it will be 26 C1, and that is going to be 26. Okay, so that's what we have. And now once I know the number of ways of my favorable outcomes out of the total number of ways, then we are able to define the probability. So we have an event A, and then now we know how many sample points are there in A. So we can define the probability, and hence we have probability of A is equal to what you'll be having 26C1 upon 52C1, and that is going to be 26 by 52, which is going to be 1/2. Okay, so here what we got the probability of event A is equal to half. That means the probability of choosing a red card is going to be half. Okay, through a well shuffled pack of 52 cards. Okay, and now let us see what is the next event we have. The next event is that the card is a face card, or the card is a picture card. So then we should know about the picture cards. Okay, so I'll define let B be the event that the card is a picture card. Okay, so this is going to be a picture card. So now tell me how many picture cards do we have? Yeah, you are good enough now. Okay, good, very good. Okay, so we have 12 picture cards, correct? And then out of these 12 picture cards, we have to draw one card. Okay, so we have 12 picture cards. There are face cards. So what will be having? Number of ways to draw a card, a face card, out of 12 cards is equal to. So it is now simple. That's going to be 12. Okay, so that's what we have. Now, what we know is once I know the number of sample points in an event, so I am able to calculate the probability of that event. So let us calculate the probability, and hence we get probability of B is equal to. So it is going to be 12C1, and this is 52C1. So we have here this is going to be 12, and this is going to be 52. Okay, so we can have this is 3 by 30. Okay, and hence what we got? So we got the probability that the card drawn is a face card, and the probability is going to be 3 by 13. Okay, so this is what the probability we have. Now let us see what is the next we have. So the card is a jack. Okay, now again we have to think. Okay, so let us define. Let C be the event that the card drawn is a jack. Okay, so now we have seen the structure of a pack. So how many jacks you have? That's very good. So you have 4 jacks. Okay, because we know there is a 1 jack in each set of cards. Okay, and hence we have total 4 jacks. Okay, so once we have this 4 jacks, so we have to choose 1 jack out of this 4. Okay, and hence what we get here, so we have 4 jacks in a pack of 52 cards. Okay, so if I have 4 jacks in a pack of 52 cards, then we can calculate the number of ways. So the number of ways to draw a jack from 4 jacks is. So what we'll be having, it will be 4C1, which is going to be 4. Okay, and once I know the sample points in any event, then we can find the probability of that event. And hence, we get probability of C is equal to 4C1 upon 4C1 upon 52 C1. Okay, so it is going to be 4 upon 52, and that is going to be 1 by 30. So here we got the probability of the event C. That means the card drawn is a jack. Okay, is 1 by 30. So here, this way, we are able to draw, or we are able to calculate the probabilities of the different events when we have the pack of 52 cards. So here, one thing you might have observed that we have not written the sample space. Yeah, because if I want to write the sample space, I have to write that all four sets, and then all I have to write the red color, and then the black color, and then the picture cards, all. Okay, so here writing the sample space becomes a tedious one, and that's why we use this idea. So we use the combination. So here, when we use the combination, that means we select the things out of the given things. Okay, and then we find the probability as usual. So, do you have any doubt in this problem or in this question? So, if you have any doubt, we can discuss it. Okay, that's great. So, you don't have any doubt. That's good. So now we are able to define the conditional probability. Okay, but before we go to the conditional probability, let us try to solve one more example. Okay, then you are able to. Okay, so we try this example. Okay, find the probability find the probability of A intersection B if probability of A is equal to zero point 0.5, probability of B probability of B is equal to zero point 0.7. Okay. And probability of A union B, okay, is equal to 0.9. Okay, so that's what we have. We have to find out the probability of A intersection B. When we know the probability of A is 0.5, we know the probability of B is going to be 0.7, and we know the probability of A union B is equal to 0.9. So here we have to go with the basic rule. Okay, so what is the basic thing that we need to understand? So I have these two events A and B. Okay, so this is event A and this is event B, and then this part becomes A intersection B. Okay, so if I want to find out the probability of this, what I know the probability of union of this. And so we have to use the formula for the probability of union. Okay, so here what we have is we have probability of A is equal to zero point 0.5, probability of B is equal to zero point 0.7, and probability of A union B is equal to zero point 0.9. Okay, and we want to find out this probability. Okay, so what we can do is then consider. Okay, what I know is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So you can see this portion, okay, of the event is counted in A also and is counted in B also. Okay, and that's why we have to be careful that this event is counted in A, this event is counted in B. So actually it is being counted twice, and that's why one time we have to subtract. Okay, so what we have now, see this figures we know. What we don't know is this figure, and that's why we want to calculate this probability of A intersection B. And hence I can write. So I can take it on the other hand side. So I can write probability of A intersection B is equal to what we have, probability of A plus probability of B minus probability of A union B. Okay, so that's what we can simplify. And now we know all these values, so we can put up these values. So what the value of probability of A? So it is going to be zero point 0.5 plus probability of B, it is going to be 0.7, and minus probability of A union B, which is going to be 9. And hence we can see that this is going to be zero point 0.5 plus 0.7 minus 0.9. So we can have this is going to be 1.2 minus 0.9, and this is going to be 0. Okay, so here we are able to calculate the probability. So we got the probability of A intersection B is equal to 0.3. Okay, and the most important rule that we need to understand is probability is never greater than 1. So that always we have to keep in mind that for any probability will never go more than 1. And the most important thing, if it is a null event, then we'll get it 0. Okay, otherwise the value is always in between 0 and 1. Okay, so I hope you got this example. So do you have any doubt in this example? Do you have any doubt in this example? No. Okay, that's great. Okay, so now we are able to define the conditional probability. Okay, and we are able to see the next examples. Okay, so let us define the conditional probability now. Okay, so we need to understand what is meant by the conditional probability. Okay, so conditional probability is that if there are two events and we know that one event had already happened, and then we expect the next event to happen. Okay, so be careful, listen carefully. Okay, so what is the conditional probability? The conditional probability means there are two events in the same sample space or of the same random experiment, and if one event had already happened and then we expect the next event to happen, then this probability is called conditional probability. Okay, so that's what we need to understand. And now let us write this in the mathematical symbols. Okay, so if I write this in the mathematical symbols, then what will be having? Let A and B are yeah, then the probability of happening event A or the event B is called conditional probability of event and is denoted as probability of A on B. Okay, so that means B had already happened, and now we expect probability of B. Okay, then again we can have the conditional probability of event B on event A is given as. So similarly, we can find the conditional probability of the event B on A. So as we'll be having probability of B on A is equal to probability of A intersection B upon probability of A. So here what we know is, since A intersection B is same as B intersection A. Okay, so A intersection B. So here I have written A on B. So A intersection B. Here it is B on A. So B on intersection A. So it is going to be same as B intersection A is same as A intersection B, and that's why we can write it like this. Okay, so this way, when we have the events A and B of the same random experiment, and then we want to find out the conditional probability of this event A and B. So the conditional probability of event A on B is given as probability of A intersection B upon probability of B, and the conditional probability of event B on A is given as the probability of A intersection B upon probability of A. Okay. Now, one more thing we need to understand, as we have seen for the independent or disjoint events. Okay, so these events are going to be uh, the event. Okay, and then if these are not in the mutually independent events, then this way we are able to calculate the probability. But what happens if these events A and B are independent? Okay, so we need to understand about this independent events. Okay, so if A and B are independent events, okay, then their conditional probability is same as pair probability. Okay. So if these events A and B are independent events, okay, then their probability will be same as the conditional probability, or conditional probability will be same as their probability. Okay. So what will happen here? Okay, in this case, that is we have probability of A is same as probability of A on B, and probability of B on A is same as probability of B. So the conditional probability is same as their probability. This conditional probability is same as their probability. But if this happens, then what will happen to the above formula? Okay, so we can see. Let us take any of this formula. Okay, and then see what we have here. So we get, what I know is the conditional probability of A on B is equal to the probability of A intersection B upon probability of B. Now what I know is these are independent events. Okay, so A and B are independent event, and hence what I'll be having, probability of A on B is equal to probability of A. Its conditional probability is same as the probability. So I can write here, this is probability of A is equal to probability of A intersection B upon probability of B. And hence I can write probability of A intersection B is equal to probability of A into probability of B. Okay, so here we get the relation for the probability of intersection. Okay, for the probability of the intersection of these two events. Okay, so we have seen when the events are not independent. Okay, then in the previous example, see, we have calculated the probability of intersection, and then we use the union formula to calculate the probability of intersection. But if we know that the events are independent, then there another way to calculate the probability of the intersection. So here directly you can calculate the probability of A intersection B as the probability of A into probability of B. So this is the formula if A and B are independent. Okay, so that's what we have. Okay, and now once we are able to understand this probability of intersection for the independent event and their corresponding conditional probabilities, then we are able to define the total probability theorem. Okay, so now once we understood the probability, conditional probability, and now we can define the total probability theorem. So, do you have any doubt in this concept of the conditional probability? So, if you have any doubt in the concept of conditional probability, you can ask. Okay, or then we can go for the total probability theorem. Okay, so no doubt. That's good. No problem. So let us see the total probability theorem. Okay, then what is the total probability theorem? So in the beginning only we have seen that the sum of the all probability of all the events is going to be one when the events are mutually disjoint events. Okay, and now suppose there is a set of a mutually disjoint event, we call it as partition. Okay, and if I have a partition of the sample space, and then over this partition I define the another event which contains smaller portions of this partition, then how I am able to get the probability of that event over this partition. So here this partition will have the intersection, non-empty intersection with this event, and then that's why the conditional probability comes into picture. And here we have to use the conditional probability to find the probability of this event over the partition. Okay, so we have to think of the probability of the event over the partition, and when we think of the probability of any event over the partition, then we have to use the total probability theorem. Okay, so let us see what is going to be the total probability theorem. Okay, so we define the total probability theorem. Okay, so here we have the total probability. Okay, so what we have here, so we have a partition. Okay, let A1, A2, A3, and so on up to AM. We have the partition. So B, the partition of the sample space. Yes. Okay. So what we have here, we have sample space. So this is our sample space S. Okay. Now I have this partition. So suppose this is the partition. So this is event A1. This is event A2, A3, and so other. So finally, we have AN. Okay. So this is the partition of this say sample space. Yes. So you can see these all events are disjoint events. Okay. So no element is common in A1 and any other set, and A2 and any other set, and like that. Okay. So their intersection is 5, but their union, if I consider, is going to be S. So that's why they form the partition of the sample space. Okay. Now, so we consider and and B be the event defined in S. Okay, so if I define any event B within this yes, so that means it will contain some part of this partition. Okay, so we can see. I'll draw the event. So this is the event B. Okay, and you can see if I draw, this is the region or the event B. Now you can see this B contains a small part of A1, it contains a part of A2, it contains a part of A3, it contains part of so and the terms, and it contains a part of AN also. So that means the intersection of this event B with the previous events may not be empty. So it may be empty, may not be empty. Okay, and hence when we have the intersection, then we have the conditional probability. And now I want to find the probability of this event B, okay, over this partition. So you can see this is the part that I have to consider, this is the part that I have to consider from A1. So that means the intersection of B and A1, the intersection of A2 and B, the intersection of A3 and B, these intersection, all intersection to be considered. And then I want only this part. So again, I have to consider the conditional probability. Okay, so here I have to consider the probability. This is the part of B and on A. So I have to consider the conditional probability of B on A. Okay, and B on A1, A2, and A3, and so on. Okay, and then I can say then the probability of B is given as, okay. So see the figure carefully, then you will understand in a better way. I want to find the probability of B. So for A1, I have to consider the probability of A1 and the probability, conditional probability of B on A1. All by having here the conditional probability of B on A1 into the probability of A1. Okay. And then I'll have plus the probability of B, the probability of B on A2 into probability of A2. So that means only this portion of this A2 I'm considering. And then so on, I can write and I can have the probability of B on AN. So probability of B on AN into probability of AN. Okay. So this is called the total probability theorem. Or in short, I can write this as the probability of B is equal to summation probability of B on AI into probability of AI when I is running from 2. So here I is running from, okay. So here we are considering the sum. So that's why this is also called as the addition theorem or total probability theorem. So we are defining event over the partition. Okay, so here we have to be careful. We are defining the event over the partition. And once I define the event over the partition, then I have to consider the total probability theorem. Okay, and now the either way, if I want to find out the probability of this conditional probability of AN over B, then what I have to do? Okay, so if I want to find the either way, the probability of AI on B, I want to find out, for example, so conditional probability of AI on B, and for that we need the Bayes theorem. So we have to understand the probability, total probability theorem, and the Bayes theorem. Okay, so Bayes theorem is slightly the either way of the total probability theorem. So we can have, this is Bayes theorem. Okay, so here the conditions are very same. So let A1, A2 up to AN be the partition of sample space years and B be the event defined in S. Okay, then, okay, so you can see as the conditions are same, but here the important thing is that we calculated the probability of B over partition, and now I am calculating the conditional probability of an element of partition over B. Okay, and hence what we have here, so we have then the probability, okay, then the probability of AI over B. Okay, so this is a conditional probability. Probability of AI on B is given as the probability of we can have here the probability of AI, okay, into probability of B on AI, because I know this probability B on AI upon the summation of probability of B. What is the probability of B we have considered? So probability of B on AI into probability of AI. So I is running from 1. Okay, so this is called Bayes theorem. Okay, so here we need to be careful. What is the Bayes theorem and what is the total probability theorem? Okay, so in Bayes theorem we calculate the probability of A on B, and in total probability theorem we calculate the probability of B. Okay, so that means we calculate the probability of event on partition. Okay, and this is the conditional probability of an element of a partition over the event. Okay, so event over partition and the element of partition over event, that we need to understand. Okay, so here we are calculating the probability of the event over the partition. Okay, and here we are calculating the probability of one partition, one event of the partition over the greater event. Okay, and that's what we need to understand. So we need to understand the basic difference between the total probability theorem and the Bayes theorem. Okay, so total probability theorem calculates the probability of the event over the partition. And what about the Bayes theorem? The Bayes theorem calculates the conditional probability of an element of event over the greater event. Okay, so that's how we have. Okay, so do you have any doubt in this two theorems? Okay, so these theorems are a little bit confusing. Okay, but we need to understand where and what theorem to be used. So when I say the probability of the event over the partition, it is total probability theorem. When I say an probability of an element of a partition over the event, then it is Bayes theorem. Okay, so this way we need to understand the Bayes theorem and the total probability theorem. Okay, so I hope you don't have any doubt. If you have, you can ask, please. Okay, that's great. So if you don't have any doubt, then let me consider